So applications of sets. Okay, let's have some problems here. The athletic director of his school has surveyed 200 students. The survey results are shown below. 140 students like volleyball, 120 students like basketball, 85 students like both volleyball and basketball. So let's draw a Venn diagram to visually understand the problem. So first, let's make this as the sets of the students who likes volleyball. Then, the sets of the students who like basketball. Take note that 85 students like both volleyball and basketball. So therefore, this number should be on the intersection of the two sets. So we should have an 85 here on the intersection of B and V. But we have 140 students who like volleyball. So therefore, the total number of students on the set of volleyball is 140. But the 85 is already taken on the intersection with the sets of the students who like basketball. So therefore, all we have to do is to subtract the whole number of students, which is 140, with their intersection, which is 85. So 140 minus 85 is 55. So therefore, there are only 55 students who only like volleyball. And same goes with the basketball. So 120 minus 85, and that is equivalent to 35. Right there. Okay, so the question of the students surveyed, how many students like volleyball but not basketball? So from the Venn diagram, the students who only like volleyball but not basketball is 55. For B, like basketball but not volleyball, we have 35. And do not like either of these sports. Okay, we forgot to put the universal set here. Let's just sum all of the students. We have 55 plus 35 plus 85, and that is equivalent to 175. But the survey is composed of 200 students. So therefore, there are still 25 students that is not on the set of V or B. So it should be put here on the universal set outside of the sets of V and B. So therefore, this number of students, 25, do not like either of the sports. So the answer on letter C is 25. So that's how we use Venn diagram in solving the applications of sets. Okay. The inclusion-exclusion principle for all finite sets A and B. Okay. Number of A union B is equivalent to N A plus N B minus N A intersection of B. Okay, let's have an example. A high school has 80 athletes who play basketball, 60 who play soccer, 24 athletes who play both basketball and soccer. How many athletes play either basketball or soccer? So we can use the inclusion-exclusion principle here. So that's the number of students, basketball union soccer is equivalent to the number of students who play basketball plus the number of students who play soccer. Then let's subtract that with the number of students B intersection S. So that's 80 students who play basketball, 60 who played soccer, and 24 who play both, which is the intersection of B and S. The answer is 116. So there are 116 athletes who play either basketball or soccer. So that's inclusion-exclusion principle. The percent inclusion-exclusion principle. So the percentage of A union B is equivalent to percentage of A plus percentage of B minus percentage of A intersection B. So that is basically the same with the earlier inclusion exclusion principle. Only that it is expressed on the percentage. Okay, let's have this example. A gourmet coffee bar conducted a survey to determine the preferences of its customers. So of the customers surveyed, 221 liked espresso, 127 liked cappuccino and chocolate flavored coffee, 182 liked cappuccino, 136 liked espresso and chocolate flavored coffee, 209 liked chocolate flavored coffee, 96 liked all three types of coffee, 116 liked espresso and cappuccino, 82 liked none of these types of coffee. Okay, these are the questions. How many of the customers in the survey like only chocolate flavored coffee? And then so on. So to answer these questions, we must express these given numbers in terms of a Venn diagram. Okay, so this is now the Venn diagram of the problem. So this is a set of all the espresso lovers. And that is equivalent to 221 all in all. Right there. So cappuccino, 182 like cappuccino, and chocolate flavored coffee is liked by 209 customers. 96 liked all three coffees. And then we have 116 like espresso and cappuccino. So this intersection of cappuccino and espresso is equivalent to 116. But 96 is already on the intersection of three coffees. So therefore, this part here is the difference of 116 and 96. So that's 116 minus 96. And same goes with the chocolate flavored coffee and espresso. That's 136 minus 96 and 127 minus 96. So to get the numbers of customers that are present in these areas here, all we have to do is to subtract the total number with these numbers here. So for the espresso, 221, the total numbers, minus the intersection, 96, minus 116 minus 96, minus 136 minus 96. And that's the total number of customers that are present in this area. And same goes with the other chocolate flavored and with the other coffee flavors. Yeah, right there. Now, if we go back to the question, how many of the customers in the survey like only chocolate flavored coffee? So that area here, that area is here. So let's solve for the numbers. Let's 209 minus 96 minus 136 minus 96 minus 127 minus 96. That's equivalent to 42. So therefore, the answer for letter A is 42 customers like only chocolate flavored coffee. Then next we have like cappuccino and chocolate flavored coffee but not espresso. So cappuccino and chocolate but not espresso. So that area is here. Let me see that once again. So cappuccino, okay, here on the other side. So cappuccino and chocolate flavored but not espresso. So we must include the intersection of the three coffees. So that is 127 minus 96 and that is 31. So the answer for letter B is 31. And for letter C, like espresso and cappuccino but not chocolate. So espresso and cappuccino but not chocolate. So this is the 116 minus 96. And that is 20. And letter D, like exactly one of the three types of coffee. So that is the sum of these numbers. So they only like one type of coffee. Okay. So that's equivalent to 142. Okay, so that's the last. That wraps up our discussion for the topic of sets. Thank you very much for listening.